Exponents.
Exponents are a shorthand notation for the multiplication of a number times itself. In other words, instead of saying 5 times 5 times 5 equals 125, we'd say 5 raised to the third power.
The 3 is known as the exponent, and the 5 is called the base. The exponent shows how many times the base number is multiplied times itself.
Here's a couple more examples of exponents.
3 to the 4th power is 3 times 3 times 3 times 3, which equals 81. In this exponent, notice we have a negative number for our base, but that doesn't change the way we find our answer. Negative 5 to the 3rd power is negative 5 times negative 5 times negative 5, and the result is negative 125.
Now, there are a few exponents which do the same thing to every base number no matter what it is. Like, any integer raised to the 1st power is the same as that integer. So 8 to the 1st power is 8. Negative 15 to the 1st power is negative 15.
There's one other exponent that is really important for you to remember. Any non-zero integer raised to the 0 power equals 1.
So regardless of whether the number is 1500 or 2, if it's raised to the 0 power, then it equals 1. One more thing about exponents that you can tuck away in your memory bank. Look at these numbers. Each time we add a 0, we go up one digit place. Now look at these exponents. Each time we increase the exponent by 1, we increase the number of digit places in the corresponding number by 1. This is just a quick note to show you how each digit place in a number increases by a power of 10. Also notice that the exponent number equals the number of zeros in each number.
Exponents are going to be helpful later on when you start dealing with extremely large numbers.
Section E, Division.
Just like subtraction is the reverse of addition, division is the reverse of multiplication.
Division is the process of breaking numbers down into equal groups. We'll look at the division of integers now and deal with other forms of division later in the program.
Now I'm going to give you an example of division at work. Over here, Missy. Let's say you got 27 people that you want beat up, right? Now, I'm a man who believes in sharing. So what I'm going to do is I'm going to divide up those soon-to-be black and blue peoples, right, amongst my 3 friends. So I'm dividing 27 by 3.
The number being divided, 27 in this case, is the dividend, and the number you're dividing by, or 3, is the divisor. The answer to a division problem is called the quotient. For our example, 27 divided by 3, the quotient is 9.
Now let's reverse the process.
If we reverse the division process and multiply the answer, 9, by the divisor, 3, we'd get 27. The dividend. Pretty cool, huh?
So, division is just multiplication in reverse. You can always check your answers by multiplying the divisor by the quotient. Just like everything else, the division process becomes more involved when we're dividing larger numbers. Picture this problem.
We'll divide 581 by 34. We're going to find out how many 34s are in 581.
First, we'll put the numbers into the proper format. The dividend, 581, goes underneath the division sign. It's being divided. The divisor, 34, goes to the left of the division sign.
What we're about to show you is called long division because there's long numbers to divide. Ready to start?
Boy, and how?
The first step is to see how many times the divisor, 34, will go into the number in the largest digits place in the dividend.
The largest digit place will always be the number on the far left, since digit places increase as they go to the left.
In this instance, the number in the largest digits place is the 5 in the hundreds place. So we divide 34 into 5. We've hit a stumbling block. 34 won't go into 5. When this happens, you must include the digit to the right, so we have to include the integer in the digits place to the right, 8. So now we see how many times 34 will go into 58. 34 goes into 58 one time. If 58 could not have been divided by 34, then we would have had to include the next number to the right in the dividend. But since 34 goes into 58 one time, then the 1 goes above the 8.
Notice the 1 goes above the 8 and not the 5. That's because 34 is divided into 58 and not 5. So the first number in the quotient goes here. The next step is to multiply 1 by 34 to get 34. You place the product of these two numbers directly below the 58. We subtract 34 from 58 to equal 24. Now we divide 34 into 24. But we first bring down the 1 in the units place of the dividend next to 24. So now we're trying to find out how many times 34 goes into 241.
The only way to find the answer to this is through trial and error. Let's try to divide 34 into 241 6 times.
To do this, we multiply 6 times 34. Then the product is 204. We subtract 204 from 241 to equal 37. 37 is left over, but the divisor, 34, can be divided into 37 because 37 is larger than 34. So, we know we can divide 34 into 241 by a larger number than 6.
Let's try 7. 34 times 7 equals 238. 238 goes beneath 241 because we're dividing 34 into 241. If we subtract 238 from 241, we get 3. And 3 can't be divided by 34. So, we know that 34 goes into 241 7 times.
There's no more numbers to bring down from the dividend, so we're done because 34 can't go into 3. But we still have a remainder of 3 left at the end of the division problem.
A division problem has a remainder when the divisor cannot go into the dividend exactly. The remainder should always be less than the divisor. If it's not, then you know you've done something wrong.
So the answer to our division problem is 17 with a remainder of 3. It's also always a good idea to check your work to make sure some minor error hasn't thrown off the whole division process.
Remember, to check a division problem, you just multiply the quotient or answer by the divisor and add the remainder if there is one. If it equals the dividend, then you know you're right. For our problem, we multiply 17 times 34 to equal 578. Then add the remainder, 3, to equal 581. Our answer's right.
We just thrown off the whole division process.
You mean the remainder's bigger than the divisor?
Yes, General.
Sir, the president's on the phone, and he wants an answer. A correct answer.
Section F, Order of Operations.
In many arithmetic problems, you'll have a long string of numbers separated by different combinations of operators. You might have to multiply, divide, and add in addition to dealing with parentheses and exponents all in the same problem. Here are some examples.
Don't worry, a standard order of operations has been developed just for these types of problems.
Of course, you need a standard order of operations to solve any problem. You have to do certain operations before others. Oh, why, just imagine. If I attack my opponent's marble field before his building blocks, oh, buddy, I'd be finished before dawn. Oh! Oh!
You always work from left to right with these strings of numbers. The standard order of operations is to do parentheses first, then exponents, multiplication and division are next, and addition and subtraction are last.
Lots of people use a mnemonic device to remember this order of operations. The first letter of each word in the order of operation spells PEMDAS.
PEMDA, 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 PEMDA.
Sinking in, isn't it?
Here's an example of a math problem that you must figure out using the order of operations to get the right answer.
5 squared plus 9 minus 3 times 4 minus 8 divided by 2. Now let's solve this puppy. Moving from left to right, we have to do any operations in parentheses first. 9 minus 3 is in parentheses, and it has a value of 6. So we substitute the 6 for the 9 minus 3. So the problem now looks like this.
Since there are no more parentheses left, we move on to the next step in the order of operations, exponents.
Again, moving from left to right, we find 5 to the second power.
Remember, the exponent is just the number of times you multiply the base number by.
So we multiply 5 times 5 to get 25. We put 25 where 5 to the second power is. So our problem now reads 25 plus 6 times 4 minus 8 divided by 2.
There are no more exponents. Multiplication and division are the next step in the order of operations.
Starting on the left, the first multiplication problem we find is 6 times 4, or 24. 24 replaces 6 times 4. We continue moving to the right and find a division problem, 8 divided by 2. The answer to this is 4, and 4 replaces 8 divided by 2. So the problem now reads 25 plus 24 minus 4.
Addition and subtraction operations are all that's left. Beginning on the left, we add 24 and 25 to equal 49. 49 replaces the addition operation, so all that remains is 49 minus 4, or 45. So, the answer to 5 to the second power plus 9 minus 3 times 4 minus 8 divided by 2 is 45. Okay? Everyone take a breather.
That was a good operation, huh?
Operations.
If you're going to use a calculator, then it's important to see if your calculator has a specific memory setup for the order of operations. In order to do a complex string of arithmetic on a calculator, you must either have a calculator that recognizes the order of operations or break up the string and only use the calculator to figure out specific operations within the string. In that case, you still need to use the order of operations.
Section G, rounding off.
All right, let's say you've got two big numbers to add, but you don't have time to get your paper out and do a bunch of carrying and so on. Well, then you can round these numbers off. Rounding off is a method used when you're not working with exact numbers. And whenever you round, you do it by digit place.
You can round off to the tens place, the hundreds place, and off to the thousands place, and so forth, depending on your needs.
Let's do an example. We'll round this number off to the nearest hundred.
Anytime you want to round off a positive integer, you have to take 4 steps.
Your first step is to find the digit place you're rounding off to. It's usually the last place you used it. For our number we're rounding, the digit in the hundreds place is a 4. The second step is to look one digit place to the right of where you want to round off to. If that digit is less than 5, you don't do anything yet. Don't move a muscle. Okay, you can move again. If that digit is greater than or equal to 5, then increase the digit in the digit place you're rounding to by 1.
We're trying to round off to the nearest hundreds place, so the digit place immediately to the right is the tens place. It has a 9 in it. Since 9 is greater than 5, we increase the 4 in the hundreds place, the number we're rounding off to, by 1. We make the 4 a 5.
If the number in the tens place had been less than 5, then we would have left the 4. There's one more step left.
We replace all digits to the right of the digit place we're rounding off to with zeros. We're rounding off to the nearest hundreds place, so we make all the numbers to the right of the 5 zeros. So our new number is 1,500.
If we want to round 1,492 to the nearest thousand, then the number would be 1,000. That's because the number to the right of the thousands place is a 4. It's less than 5, so we skip to the next step and replace all numbers to the right of the 1 with zeros.
You can round off any integer, no matter how large it is, if you use the steps we've just talked about.
What if I want to make up my own rules of rounding?
Section H, scientific notation.
Another method used to make calculations with large numbers easier is scientific notation. Remember we said earlier that each digit place of an integer is represented by a power of 10. 10 to the first power is 10. 10 to the second power is 100, and so on. In scientific notation, you multiply a number between 1 and 10 by one of these powers of 10. Let's do an example. We'll express the number 2,000 in scientific notation. 2,000 in scientific notation is 2 times 10 to the third power. How do we know this? Well, there's 3 zeros in 2,000. And like we said earlier, the amount of your exponent is always equal to the amount of zeros in your number. So we know the exponent's 3. 10 to the third power is 1,000, or 10 times 10 times 10. Now we just multiply 1,000 by the first digit in the number we're trying to express. In this case, the first digit is a 2. 2 times 1,000 equals 2,000. So 10 to the third power times 2 equals 2,000.
I know all of you out there want to do another. Quick! Represent 400,000.
First, we count the number of zeros to determine what power of 10 you're working with. 1, 2, 3, 4, 5. The number of zeros you have in your number is your exponent. There's 5 zeros, so 5 is your exponent.
Okay, we're halfway there. We know our power of 10 is 5, or 100,000. Now that we have the right number of digit places, all we need to do is multiply 100,000 times 4, the first digit in the number we're trying to express, to get 400,000. So 400,000 in scientific notation is 4 times 10 to the fifth power.
Remember that the amount of zeros in the number is the same as the power of 10 we're raising it by. No matter how large the number is, you can find the power of 10 it's multiplied by if you count the number of zeros. That's why this method comes in so handy for scientists studying vast distances in the galaxy.
Johnson! How are you, buddy? I think I'm gonna build that deck this weekend.
Really?
Yeah.
On the back of the house?
Oh, you know it.
How big are you gonna make it?
I was thinking 2 times 10 to the first, by about 5 times 10 to the first. Big deck, big deck.
Wow. You're probably gonna need about 6 times 10 to the second nails for that one, huh? Right? Huh?
Yeah.
Yeah.
And one other thing to remember about scientific notation. Remember that a large number is in scientific notation when it is written as a number between 1 and 10 multiplied by a power of 10.
Oh, like 4 times 10 to the fifth power. 4's between the 1 and the 10.
Quiz 2.